Our next lesson is going to be on equilibrium and reversible reactions. So you're going to need those set of notes, reversible reactions and chemical equilibrium notes, which you either have on paper from before spring break or you can download right above this. You'll also, of course, need a writing utensil. So chemical equilibrium. So let's start off with a story here. In the early 1800s, late 1700s, early 1800s, Napoleon Bonaparte of France decided that he wanted to invade and conquer Egypt. And so in the process of doing this, he was, among other things, very interested in ancient Egyptian civilization. He saw it as being like the cradle of Western civilization and was interested in mummification. The ancient Egyptians used to take their pharaohs and other important people and would mummify them. And to do that, it required certain materials, one of which was a material called natron. And so what Napoleon did is that he invited along on his military expedition a number of scientists, including a scientist named, a chemist named Claude Louis Berthollet, to try to investigate how the Egyptians went about with this process. And so Berthollet, when he came with Napoleon, and here is Berthollet right here, found out that the Egyptians were able to find natron from these lakes that were out in western Egypt called the Natron Lakes. And so when he went to the Natron Lakes trying to find where natron came from, he discovered a couple things. He discovered that natron forms along the shoreline of the lake. We can see some natron mixed into this foamy material on the shoreline. And he also was able to identify a couple other things. First thing, these lakes were saltwater lakes, very salty lakes, had salt as sodium chloride. Natron is a chemical called sodium carbonate, and he was able to identify that the rocks that surrounded the lake bed were made of limestone, which is calcium carbonate. And so he said, thinking about this, he was aware of a chemical reaction that was commonly known by chemists in the lab that worked like this. Na2CO3 plus CaCl2 yields 2NaCl plus CaCO3. The Na2CO3 is the natron. If you react that with CaCl2, calcium chloride, it will produce salt and calcium carbonate, salt and limestone. Now, here's the problem, is that Berthollet had found in his lake not that if you reacted natron with calcium chloride, it would give salt and limestone. He had found the reverse reaction, that if you had a saltwater lake surrounded by limestone, then it would produce natron and calcium chloride. And so this was something that was unique, that had never been discovered by chemists before. A reaction that didn't just go one direction, but that went two directions. It could either react from the natron and the calcium chloride to produce salt and calcium carbonate, or it could react from calcium carbonate and salt to produce the natron and the calcium chloride. So this was the first what we called to be a reversible reaction, a reaction where the reactants can react to become the products and the products can react to become the original reactants. In some sense, they're both reactants, they're both products. We indicate this with a set of double arrows. So that shows that these two substances can react to form these two substances, or these two substances can react to form these two substances. And so this is one that can go both directions. Now, to understand how these reactions work, we're going to use an analogy. So one question we ask about these reversible reactions is it like a ping pong game, that the things on the left react to become the things on the right, and when they're done, they react to become the things on the left, and just go back and forth? Or do these reactions happen simultaneously both directions at the same time? Well, a way to think about it is to imagine a stadium with people in the stands and some restrooms. And so for some strange reason, they've decided to have put only two sets of restrooms, just one set of restrooms for the stadium. And so what's going to happen is the people are going to fill up the stadium, and once the stadium fills up, let's say they open up the restrooms. people will flow from the stands into the restrooms. The reaction in this case, we would say, would go to the right as people move from the stands into the restrooms. But it's not that everyone will move into the restrooms, and then once everyone's done the restrooms, everyone will move back to the stands. What instead is going to happen is people are going to flow both directions, is that 5 people will go into the restrooms, and at the same time, maybe 3 people leave the restrooms and go into the stands. And maybe as the game ends, 10 people come out of the restrooms, but only 2 people flow into the restrooms. The reaction, in quotes, between people in stands and people in restrooms is a reversible reaction. People can go from the stands to the restrooms, people can go from the restrooms to the stands, and they both happen at the same time. There's no reason why people only go from the stands to the restrooms or only go from the restroom to the stands. People are constantly going from the stands to the restrooms and constantly going from the restrooms to the stands. Now, if we think about this, over time, we recognize that just because the number of people there are people going to the stands to the restrooms and restrooms to the stands does not mean they're equal amounts of people in the stands and people in the restrooms. Obviously, the stands hold a lot more people than the restrooms do. Let's say the stands hold a total of 10,000 people and the restrooms hold a total of 100 people. It's still, what's going to happen is we're going to get to the point where the number of people flowing into the restrooms is the same as the number of people flowing out of the restrooms into the stands. So let's say that we fill up the stadium, 10,000 people, before we open up the restrooms. Well, as soon as we open up the restrooms, more people will flow into the restrooms than will flow out. And that's obvious because of the fact there are no people in the restrooms at the beginning to flow out. So this reaction would start off by going right. There might be 10 people per minute going into the restrooms for the first minute and no people coming out. But as people flow into the restrooms, the number of people in the stands goes down and the number of people in the restrooms goes up. And as the people in the restrooms goes up, people are going to start flowing out. So maybe in the third minute after the restrooms are open, there's still 10 people flowing in, but there are 2 people that are flowing out. And so then, and maybe by the 5th minute, as the restrooms have filled up more and more and more, is that now there are 10 people flowing in and 8 people flowing out. But eventually we'll get to the point where the number of people going into the restrooms is the same as the number of people going out of the restrooms. And when this has happened, we would say that this restroom stands reaction has reached equilibrium. It's reached a balance where the flow in and the flow out are going to be the same. Now, note that does not mean there are the same number of people in the restrooms as there are in the stands. Maybe the restrooms have filled up. They have 100 people inside of them, and the stands will now have 9,900 people inside of them. But still, what's going to happen is that 10 people flow into the restrooms every minute, 10 people flow out of the restrooms every minute. And once that happens, the total number of people in the restroom and the total people in the stands is going to stay the same. We would say their concentrations are going to stay the same. The number of people in the space does not change anymore, even though the reaction continues. And so this is what we call a reaction at equilibrium. So a reversible reaction is in equilibrium when the reaction rate to the right equals the reaction rate to the left. How fast the reaction is going to the right is the same as how fast the reaction is going into the left. This means the concentrations of the substances no longer change. In the same way that once there was a balance, the rate of people going into the restroom was the same as the rate of people going out of the restroom, the number of people in the restroom was going to stay constant, even though it's not the same people. Is that the people are constantly changing, but there are always going to be 100 people in the restroom as long as 10 people flow in and 10 people flow out. Because for every 10 that leave, 10 come in. The same thing would be true if instead of 10 people coming in and 10 people coming out, it was 20 people coming in and 20 people coming out. As long as the rates in both directions are the same, the concentrations of people in both places will stay the same. And that's going to be true for chemical reaction at equilibrium. The rate at which Na2CO3 and CaCl react to go to the right is the same as the rate at which NaCl and CaCO3 react to go to the left. And as long as that's true, the concentrations on the left and the concentrations on the right will stay the same. Now, be careful. That doesn't mean the concentrations of the two on the left are the same as the concentrations of the two on the right. They could be very, very different. but they'll stay the same. So maybe we end up with a concentration of, like a 70% solution of these and a concentration of only a 5% solution of these. And that's okay for the same reason that we saw before with the stadium and the restrooms. It's okay if there are 9,900 people in here and only 100 in here. You could still have the flow going in and the flow going out staying being equal, which means the concentrations will stay the same. And so that's what we mean by equilibrium. It's in equilibrium if the reaction rate to the right and to the left are the same, and if it's at equilibrium, the concentration on the left and the concentration on the right will stay constant. It will no longer rise or fall, but that doesn't mean the concentration on the left is equal to the concentrations on the right.